Okay. Any questions from anyone before we get started? Lab 1 seems to be going pretty well for people. Everyone's been doing okay hitting the checkout so far. The lab sounds crazy. Sounds like a ton of birds. I can hear the lab from like all the way on the other side of the building. It sounds awesome. Some crazy sounded birds too for people that are debugging, like lasers. I wanted to start today just by going over. Yeah, I've been spending a bunch of time with folks in lab, and there are a few common bugs that I'm seeing from like group to group to group, and I want to take the time in here to just go over those bugs. For some of you, this is going to be a little bit of a review because we went over it in lab, but I feel like it's a good idea to see these same bugs explained outside of the stressful environment of lab. Maybe it helps internalize things. One of the common mistakes that I'm seeing, not a mistake, but a common bug that I'm seeing is we talked last time about how to do this sound synthesis, we have a strict timing deadline to meet to get through this interrupt service routine. We have to get through this interrupt service routine in 909 cycles, actually a little bit less, right? Because it takes a few cycles to get into the ISR and a few cycles to get out, about 70 to get in, a little less to get out. So there's something like, I don't know, 850 cycles to spend or so in the interrupt service routine. And what I said last time was a completely sort of naive implementation of the equations that we use to calculate the target frequencies, a floating point instantiation of both of those equations. You won't finish those calculations in time to get through the interrupt service routine in time. The symptom of this that you might experience, depending how badly you're using timing, you might hear a swoop or chirp sound that sounds kind of weird in a way that's difficult to describe, kind of scratchy. That's one symptom. Or alternatively, your whole CPU will lock up. And the apparent symptom might be something like my TFT stopped working. What's actually happening is you're consuming all of your time in the interrupt service routine and no code is executing in main anymore, which means the code that's running the TFT is not executing anymore and the whole thing locks up. So if you have like a counter running on your TFT, you would see it stop and no sound would come out. And one of the places that I pointed folks to save yourself cycles is to look for the places where you're doing floating point division between constants and create a variable or a macro that is assigned the value of that constant. And then instead of doing that floating point division between two constants every time through the ISR, plug in that variable. And you're going to save yourself the amount of cycles associated with the floating point division, which is a lot. And one of the places where this appears every time is in the computation of this DDS increment. So in lab 1, you use the swoop and chirp equations to compute your desired F out. And then to get your DDS increment, you multiply that desired F out times 2 to the 32 over Fs. That 2 to the 32 over Fs is a floating point division, and it's expensive. A good idea is to create a variable or a macro that is assigned the value of 2 to the 32 over Fs, and then every time through the interrupt to plug that in. Something to be careful about is if you choose to use a macro, something like this, something that I've seen a few times is folks doing something like pound define, we'll call it maybe DDS constant, and then saying 232 over Fs. And then using that macro DDS const in the ISR. People know what the problem with this is. Okay, it sounds like I'm getting a lot of nods because we talked about it. The problem is the way that these macros work is it is a textual replacement of the macro name with the text on the right. So in the ISR, wherever, in this case, DDS const appears, it's going to replace that string of characters with 232 over Fs. So if we do this, then we're not actually saving ourselves a floating point division because it's just plugging in the same expression that we had before and doing that floating point division every time. Right? So I've seen this a few times, so just keep an eye out on this. The solution, there are a few possible solutions. One might be to make DDS const a variable instead of a macro, and to assign it the value 2 to the 32 over fs, so it's only computed once and then reused. Or alternatively, you do that division on a calculator and get the number, and you create a macro with the number there that division actually evaluates to. Does that make sense? And by the way, I've seen a few other people do this as well. You can create macros that take arguments. So maybe we would define some macro like square, which would take some argument, oops, a times a, right? Where you could call some macro square with an argument a, and it would replace that expression with the argument times the argument. It kind of feels like a function, but it's not a function. Do people know what is the advantage of doing stuff like this as opposed to sometimes creating functions? Yeah. Yeah, exactly. So there, you made 2 points there, both of which were correct. One is it can improve readability, which is debuggability, right? It's good to have readable code because readable code is debuggable code. And the other thing that it does is because it's just a textual replacement, you aren't going into a function, doing some computation, and then leaving that function. Getting into and out of a function has some overhead associated with it. So sometimes, depending what you're doing things like this can save you cycles. Same true of inlining functions. That will also save you some cycles. Any questions or comments about that? Yeah. Inlining is essentially the same as this, where you can declare an inline function where the compiler, instead of going into that function and then coming out, it will put the contents of that function in place. It's very similar to a macro. Yeah. Yeah, I think that's the right vocabulary, a macro.
Yeah, so I don't understand how it's faster than just writing like 8 times a day.
It's not. It's not. Readability, yeah. Or, the other reason you might do it with something like a constant is if you have some crazy constant, like say 2 to the 32, that appears lots of places in your code. If you type this a bunch of different places, you will have an error, right? Like you will make a mistake. So it improves readability and it makes your code less error prone in the event that you have crazy constants. You type them in correctly once and then use the readable, less error prone name throughout the code. Same true of maybe some complex expression. Make sense? Okay. Another error that I've seen a few times is folks you enter the interrupt service routine, right? You need to compute the desired output frequency at that time, where time, as we've talked about in this lab, the unit of time that makes sense for this lab is number of interrupts. So you have some incrementing variable inside of your interrupt service routine that's keeping track of how long have I been producing this sound. And your desired output frequency is a function of that variable. So in the lab 1 demo code, there's a variable that many of you have been using called note time that's doing exactly that. It's counting up, and you are using that variable to compute as a function of that note time the desired output frequency at that time. So in this expression for the swoop, y here is f out, your desired output frequency. X would be that variable note time, which is also incidentally being used to compute the amplitude envelope. Something to be careful about is if you have your code set up such that this expression and the chirp expression is being computed every time you enter the interrupt service routine, regardless of whether or not you're producing a sound, then as the value of note time increases without bound, the amount of time that it takes to finish that computation also increases. So we've seen this bug where you hit reset, it produces one swoop, and then the TFT slows down and dies. And the for that is if in your ISR you are allowing for note time or whatever variable you're using to increment and keep track of how long you've been producing a sound, if you're allowing that to increase without bound, the amount of time that you spend computing this will also increase, and you'll end up missing your timing deadlines, and the thing will slow down and stop. The solution is in the code. Don't allow note time to increase without bound. So put this inside of some conditional. If note time is less than the total length of the sound, which is 5,720 interrupts, then increment it. Otherwise, just don't increment it anymore. Or be careful that you're only ever actually executing those computing the desired output frequencies if you're actually producing a sound. That's another solution. One more bug I've seen is I've seen some people, I've heard some bird songs that sound correct but cut off. And the reason for that in many cases has been the amplitude modulation. Remember that your amplitude modulation, you ramp up the sound, it sustains for a while, and then it decays back down. And in the example code, the amount of time that you spend ramping up, sustaining, and decaying is controlled by these variables: attack time, sustain time, and decay time. If these don't sum to the total length of your swoop or chirp, 130 milliseconds, 5,720 ISR cycles, then your amplitude modulator is going to cut off the sound early. So make sure that these sum to 5,720. So maybe you do an attack time of 1,000, a decay time of 1,000, and a sustain time of 3,720. And then look at the output on the scope, use the cursors to measure the length of that sound, and make sure that it is precisely what you want, 130 milliseconds. Questions? Okay, I have a couple more sort of questions to answer. One is related to lab reports. Some people are starting to work on lab reports, which is great, or they gather materials for lab reports. I just want to remind people that if you go to the policy page, there's a whole section here on what is expected in the laboratory report, and there's some examples included. So you can read through this to figure out what goes in the lab report and what you should include. Some quick comments that I'll make about this as people get started is a common question I get is, what's the expected length of these things? And how much detail should I include? And you can use the examples to help answer those questions. But generally speaking, the advice I like to give is consider the target audience for your lab report to be yourselves in maybe 3 years, and assuming that you haven't been working with PIC32s in the meantime. Right, so the target audience is someone who has a background in this material, but maybe those neurons have lost some connections, right? So you've forgotten a little bit. You should write with a sufficient level of detail that you could open up your lab report 3 years from now, recreate what you did, and understand why you designed it in the way that you designed it. And as you're putting things together, putting your lab report together, try to think carefully about the best way to convey different types of information. Right, so something that I see a lot in lab reports is a wall of text to describe a state machine. Text is not the way to describe a state machine, right? Make a flow chart. Make a flow chart diagram that shows how your state machine works. Add some text to explain what's going on in that diagram. But a diagram like that is really what makes sense to convey that type of information. And think carefully about the other aspects of your project. What's the best way to convey the information I'm trying to convey? It's a good skill to practice, right? So don't just sit down and start writing like crazy. Think carefully about how to represent the information in the clearest way. Yeah.
Can you remind me, is it one lab report per person or one lab report?
One per group, one lab report per group. And the lab reports will be due. So suppose you are in the Wednesday afternoon section. That means your lab 1 final checkout will be by the end of the Wednesday afternoon section next week. So your lab report would be due at the beginning of lab section the next week. So they're due at the beginning of section a week after your checkout. The policy page contains all of the stuff that's included in every lab report. And then for each lab assignment at the bottom of the lab write-up, there's a few incidental other things to also include specific to that particular lab. For this lab, one of the things that we asked for you to include is a spectrogram of the sound that you produced so that you can compare it to the spectrogram of the actual bird. And there are a few ways that you can do this. There's an easy way and a more difficult way. The more difficult way to do it is you can take the, right now you have the aux, the DAC output from the PIC going into an audio jack, and you have that going to speakers. You can replace that connection with an aux jack into the microphone input of the lab PC, record an audio recording of you creating swoops and chirps, import that into MATLAB or Python, and create a spectrogram. Alternatively, we have installed on all the lab PCs a free software called Waveforms that allows for you to use the sound card on the lab PC as an oscilloscope. This, by the way, is just a good electrical engineering trick to know. If you are at home and you need an oscilloscope and you don't care that much about sample rate, if you're okay with lower sample rates, as long as you keep your voltages in a safe range, you can use the audio card of your computer as an oscilloscope. But I want to show you how this works just so that people know. So I've joined the Zoom call that's recording this from the PC in my office, which is set up like a lab PC. And this is set up with exactly the same code that you all are putting together. It's just instead of the keypad, I have a serial interface so that I can do it from here. But what I want to show you is if you open up the Waveforms software and select the sound card as your device. Oops. Thank you. I have some settings loaded here. It will create a little, what looks like an oscilloscope here. Oh, why won't you work? Well, I'm not going to spend time debugging this, but the point is, there is software available on here that you can use to create these spectrograms automatically. Was working right before class started, but very predictably, it's not right now. So that's okay. But this is how you do it. You can open up Waveforms, plug it with an aux jack from your PIC into the microphone input of the PC, and this software will create spectrograms for you. And then you can compare those to the spectrograms of the actual cardinal and see how they look. Question?
Yeah, so what is like the safe range between like 5 volts, like 5 volts?
Is what's the safe range for the audio input of your PC? 5 volts, I believe. Bruce?
It's probably safe plus minus 2, rated at plus minus 1. Standard line.
There you go. But in a bind, it's a good trick for sure. One other thing I wanted to mention, I've heard some people, there's this question in lab 1 of you need to be able to put the device into a playback mode where you push keys and they produce sound, swoop, 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 chirp, 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 and then a record mode where you record a sequence of presses, release a button or move a switch, and it plays the whole thing back. And the question is, how long of a song do I need to record? That's not something that I specified, so it's up to you. And you may, it does not have to be, it can't be an arbitrary length song. So maybe 50 sounds, right? Long enough to at least record the song that we're trying to simulate. I've heard some people have been tempted to use malloc to dynamically allocate memory. Do not do that. You'll shoot your foot right off. The reason that that's unsafe on something like a microcontroller is a little bit subtle, but you can end up, see if I can briefly describe it. So when you call malloc, you're reserving some chunk of heap, right, which is part of RAM. You could reserve, reserve, reserve. Depending which part you free, you end up with gaps in your heap. And if you have a bunch of these, people are nodding, you know what I'm talking about. So you end up, the problem ends up being my program is crashing. I don't know why, and it's doing it at random times, which is just the worst bug in the world to try to track down, right? So don't use malloc. What you should do instead, and this is true generally of microcontrollers, is you know how much memory you have available, right? So suppose you wanted to store the longest possible song that you could store on the microcontroller. The correct way to do this, if you wanted to do that, is figure out how much memory you have left and pre-allocate that amount of memory for song storage statically. And then don't do any dynamic memory allocation during runtime. You want for your code to be highly deterministic for these sorts of systems. So figure out how much memory you need a priori before the thing even runs. Figure all that out, allocate everything yourself, and then don't dynamically change those things while the system's running. Yeah. Yeah, yeah. You know how big everything is. You know where everything is in memory. You're not dynamically changing things as the thing's running. Questions about that? Do I have any more comments about that? I don't think I do. Oh, the other thing I wanted to mention, this is with respect to the timing in the ISR, because there have been a few groups who they produce a sound and they go, I don't know if that sounds right or not. And I've been listening to so many goddamn swoops, I can't tell anymore. So, so if you really want to figure this out, keep in mind that we are doing this audio synthesis in a timer interrupt, specifically the timer 2 interrupt. So that means when timer 2 overflows and resets to 0, the interrupt flag is thrown. And we'll enter the ISR. It's going to take a certain amount of cycles to get into the interrupt service routine. I think it's something like 70. I measured this, but I can't remember. It's 70-ish. 70-ish cycles to get into the interrupt service routine. And then however many cycles it takes for you to do all the DDS computations and get out. If at the bottom of your interrupt service routine, you make a plib function call to read timer 2, which is going to return. So you'll put this in some int like ISR time, which would be an int which you previously declare. But if you read timer 2 at the bottom of the interrupt, what that's going to read out is the amount of cycles that it took for you to get into the ISR and get to the bottom. Store that in a variable, and then down in your thread, print it to the TFT display. And that's going to give you a quantifiable. That is going to quantify how much time you are spending in the interrupt service routine. And the other cool thing about this is if you're working on optimizations, which some groups have been very obsessive about, which has been awesome, it allows for you to actually measure how good your optimizations are. How many cycles am I saving by changing, this particular operation to a series of shifts and adds, right? Instead of doing multiplies or something like that. You can actually measure that. So if you're not sure if you're hitting timing deadlines, even if you are sure, frankly, because it's interesting, read timer 2 at the bottom of the interrupt service routine and print it out to the TFT display. Yeah.
So, you know how we said no time equals 0 to kind of triggers the sound?
Yeah.
Is that just resetting the envelope so it's not zeroing out the ISR all the time?
Yeah. The question is, what people have figured out is the mechanism that starts a sound production in the demo code is zeroing this variable note time. The reason for that is if we look at line 126 here, this is where we're computing the data that we're sending to the DAC. And what you can see is the data we send to the DAC is the value that we get from the sine table, which is the direct digital synthesis stuff that we spend a bunch of time on, multiplied by that variable current amplitude, which is the amplitude envelope. And in this set of conditionals here, you can see that under some conditions, current amplitude is set to a non-zero value, and other conditions it's set to a 0 value. Those conditions being the value of note time, the amount of times we've been interrupting, is less than attack plus sustain plus decay. So if we're still in the sound part, amplitude gets a non-zero value, otherwise it gets a 0 value. The point being, if you zero this, so that this goes back to 0. It'll start counting up from 0 again, and it'll produce a new sound.
So when like after we play a sound, it's still going into the ISR and trying to output sound, it just gets zeroed out.
Yeah.
Okay.
Yeah.
That seems kind of inefficient.
It's what seems inefficient.
The fact that you're going in ISR to produce no sound.
So once you set up that interrupt service routine, it's just going to go. And what happens each time you enter, you want to depend on whether you are producing a sound or not producing a sound at that time, and how far into that sound you are.
Yeah.
And those parameters that affect that flow through the interrupt service routine will be controlled by the threads.
Yeah, but I mean, the timer is what like continues to make it through the ISR, right?
Yeah.
So can we set up? I know we need the timer because we need precise timing for this application. But I think when we're getting to precise timing, it would be a better idea to like not enter the ISR.
I mean,
Every time you put the button on some pin, it enters.
I think I see what you're saying. So this feels like a question about polling versus interrupts, kind of.
Yeah, like when I think of interrupt, I think more of like IOs, right?
Sure. So you could, we have a timer interrupt set up here. You could set up an interrupt also on an IO port, so that a rising edge on an IO port triggers an interrupt, and then some action is taken, which is nice for saying in some, sleep or low power mode until some condition is met that changes your mode. For this kind of application where we care about timing, the interrupt is what makes sense. Bruce, did you have a comment? So the next thing I want to talk about is the debounce state machine associated with the keypad. Actually, I'm going to start in the code here. Last time we talked about how the keypad scanning takes place. And if we have time, I'm going to revisit that because I feel like I just created confusion last time we talked about this. But in any case, I'll revisit that if I get through the state machine in time. What's happening in this keypad thread is within the while one loop here. So this is the stuff that happens every time we enter the thread. We yield for 30 milliseconds. We go through and scan the keypad. This is the stuff we talked about last time. When we scan the keypad, we're getting a key code. So we're reading the IO ports on the port expander and getting a key code. And then we are seeing if there's a match between that key code that we read and any of the key codes associated with valid button pushes. And if there's a match, then the value of the key that was pressed is stored in this variable I. Okay, so by the time in the example code you get down below line 330, this variable I will have a value of -1 if there's no button pushed or if there's a valid button push, buttons pushed at once or something like that. Or it will have a value of 0 if 0 was pushed, 1 if 1 was pushed, 2, 3, 4, 5, 6, 7, 8, 9, 10 if star was pushed, and 11 if pound was pushed. Okay, so this variable I is the decoded key press for this time through the keypad thread. You will need to, the requirements of the lab are 1 sound per button push. So that means I can push and hold the button. I can push and hold the swoop button, it just goes swoop. And I can hold it as long as I want and 1 sound is produced. I can push and release it as fast as I want, and it's only going to produce 1 sound. I can double push and it'll push 2 sounds. This is going to require you're going to have to debounce the keypad. The keypad is a mechanical system, right? It's a spring mass damper system, so it oscillates and it may bounce. which means when you push and I is reading -1, right? So we're not pushing, I is reading -1. When I push the 1 down, for the first scan through, it might read I is 1, and then it might bounce off of the contact and read a -1 again, and then bounce back onto the contact and read a 1 again. And you need to account for this, because if you don't, you're going to hear swoop, swoop, which is not what you want. So you can do this with a relatively simple state machine that I want to talk through. A relatively simple state machine that I want to talk through, which is going to be composed of 4 states. We're going to have a not pressed state, which is to say no keys are pressed, right? And we're going to have a pressed state, which is to say a valid key is being held down. And we're going to transition from the not pressed state to the pressed state and back through 2 intermediate states that we'll call maybe pressed and maybe not pressed. And the representation that I'm using here is each of these circles represents a state. The top of the circle is going to be the name of the state. The bottom of the circle, I'm going to put the tests that will run in that state to evaluate whether we're going to do a state transition. So on reset the pic32. We'll enter the keypad thread for the first time and get a key code. The variable I will assume a value, either -1. Well, actually, we're going to assume that the user is not holding down a key and pushes reset. So we're going to scan the key code, and when the first time through, we're going to be in the not pressed state. The question that we'll ask ourselves is the value that we get from the key scan -1, which is to say, does that variable I have a value of -1, which indicates no key is pressed or there's an invalid key press? If the answer to that question is yes, then we just stay in the not pressed state, right? No key's been pressed. If the answer to that question is no, then we're going to do 2 things. We're going to transition to a state that we'll call maybe pressed. And we're also going to store the value of the key scan that we just read that was not equal to -1, right? Maybe we scanned the keypad instead of -1, we read 2. We're going to store in a temporary variable that we'll call maybe possible, just to say the possible value of the key, the value of the key code just read, and this maybe pressed state, rescanning the keypad when we are in that state. When we're in the maybe pressed state, we'll ask ourselves, we're going to come back into the thread associated with the keypad, get a new value for I, the decoded key value, and we're going to ask, is our new key code that we just read equal to the one that we just stored? Do we have 2 subsequent keypad scans, both yielding the same valid key code? If the answer to that question is no, then we go back to the not pressed state, because that means maybe the key is bouncing. So maybe we weren't pressing a key, the key code was -1, we pressed 2, so we read the key code is equal to 2, went up to the maybe pressed state and stored the value of 2 in this variable possible. Then the key bounced. So on the next scan, we read a -1 again because it bounced off the contact. So the answer to that question was no. We go back to the not pressed state. Energy will dissipate in the meantime, so now it won't bounce again. It'll have nice clean contact. We'll read a value 2 again for the key code, transition up to the maybe pressed state, ask this question again, and if we're not bouncing anymore, we're going to get a valid answer. We're going to get 2 subsequent reads that are the same. In that case, we'll transition from the maybe pressed state to a pressed state. And it's on this transition, on the transition from maybe pressed to pressed, that you take some action. Produce a sound. If you're in record mode, you log a sound, a key press. It's on that transition from maybe pressed to pressed. Not in the pressed state, because then you're going to get swoop, 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 right? It's on the transition from maybe pressed to pressed. So now we're in the pressed state. Re-enter the keypad thread, scan again. We ask, does the key code that we read, the new value of I that we just read, still match the one that we stored? Just to say we're still holding the key down. If the answer to that question is yes, we stay in the pressed state. If the answer to that question is no, we'll transition to some maybe not pressed state. Scan again, get another value for I. for the key code. Ask ourselves again, does the key code equal the one that we stored? If the answer to that question is yes, then we go back to the press state. Maybe we were holding down 2, so I was equal to 2. We released it, so we got a value of -1, and then it bounced. We got a value of 2 again. It'll bounce back off, and energy is dissipated now, so it's a clean release. We'll read -1 and transition here. We'll ask ourselves again, does the key code equal possible? If the answer to that question is no, then we'll transition back to the not press state. So 4 states. And if you set this, so where is this going to live? This is in all likelihood going to end up being a series of switch cases.
I didn't get that. Could you
Whoa.
try again?
We need to explain the state machine.
Okay, so your debouncer will go, the keypad debouncer state machine will go here. After you've got the value for I, the decoded key value, you'll use that value to build this state machine. So your series of switch cases will live down there in that section. Questions about that? Yeah.
Okay, I guess this is more of a question about running. So when we're running the state machine, and do we incorporate a delay between the button checks? So like each transition error, it's typically like we make sure that we wait around like 30 milliseconds.
Yeah. So we scan the keypad every 30 milliseconds. There's a 30 millisecond delay between each scan of the keypad. Why 30 milliseconds? Because if you sit in the lab and push the key as fast as you can with a scope, you can't do that faster than 30 milliseconds. I definitely can't. I can't even, I can do it like, this includes some margin, right? I can't get close to that. So that's why. So this amount of time is one that is calibrated such that it is too fast for humans to screw up the state machine. And also, you know, a related question is, this state machine accounts for, does it account for 3 bounces? I think it does actually. Never mind. It does actually, I think. Yeah. Yeah. Right, right. Correct.
So I guess my question is then, in the context of writing, right? If we write it to scan every 30 seconds, how do we get stuff to run for the same day? And then it scans, and then it waits 30 seconds, but it's waiting, at least in our code, to do that while it's interrupted. At least that's what I still can't get in my head.
So you're probably going to have a couple threads in your program, probably 2. And what the scheduler is going to do is look at the first thread and ask, are you ready to run? If the answer is yes, it'll run, and the other one won't run until this one's complete. And then I'll ask this other one. The PT yield time for 30 milliseconds says it's going to say, I'm not ready to run for 30 milliseconds. And then after that amount of time has expired, the next time the scheduler gets to it, it'll say, I am ready to run. So, but this is part of the reason that if you care about precise timing, like for audio synthesis, you don't do that timing with threads, right? Because you're telling the thread to yield for 30 milliseconds, but you don't know how long it's going to take for the scheduler to get back to that thread. The other one might be running for a while. This is in contrast to the interrupts, which will interrupt the threads at precisely the rate that you dictate. So we set up the interrupt service routine to produce the sound because no matter what the lazy threads are doing, they can be taking their time doing whatever they're going to do. The interrupt service routine is going to jump in at just the right time, do the time sensitive stuff, and then leave and allow the threads to do the things that they were doing. So we put the slow stuff, the human stuff, right? The things that involve like physics with meaty fingers, we put that in the threaders because we don't care that much about precise timing. We're doing human level timing, which is so slow. The precise stuff we put in an interrupt service routine. Possible, explain possible. Well, all that is that's just a variable that we're using to store the value of the key code that we read that caused for us to transition from not pressed to maybe pressed. So say we were sitting in the not pressed state, we kept reading a key code of -1 because no key was pressed. We pressed the key 2. So key code's going to assume a value of 2. When we transition to maybe pressed state, we'll store a value of 2 in this variable possible, so that when we're here, we can ask, okay, on the next read, did we get another read of 2? It allows for us to remember what we just read.
How do you tell the other thread that's not the one that's running? What are the commands to say that like it's finished? And how do you know when you should go back to the?
So consider setting this up is you might have one thread that's responsible for reading the keypad and another thread that's responsible for setting the direct digital synthesis parameters in order to produce the desired sound or sequence of sounds. So if you set it up that way, then what you would like is for the keypad thread, depending on if you're in record mode or in play mode, you want for the keypad thread to either log a key press, probably in some array, some encoded value for a sound, maybe 0 means swoop, 1 means chirp, 3 means pause. So you either want for it to store a key press, or in the case that you're in playback mode, you want for it to signal the other thread to go through and set DDS parameters and produce a sound before it comes back and scans the keypad again. You could do this with the proto-threads environment allows for you to set up semaphores, which are objects that are used for between thread signaling. It's a way for one thread to signal another thread to run, and for this thread to wait until it is signaled by this thread to run. Or, you could use, what is a semaphore? Basically, that's a Boolean flag, really. You could use your own Boolean flag and set up a similar set of logic. That is, you could basically use the built-in semaphores or create your own version of a semaphore. But there would be some mechanism by which one thread would signal the other thread to run, and the other thread would wait until it was signaled to run once, and then wait again until it's told to run again.
So you would just do like a while loop with like while flag.
You would have it on that proto-threads page. There's a series of, you can have it yield. The yield commands, there's a bunch of different yield commands.
You can do a yield that has a Boolean.
Yeah, you could do, there's an option for a yield until, and then you put a logical expression in the yield until. Yep. Other questions? Questions about how to arrange your code? Do people have a decent sense of which threads they might create and how they're going to get those threads to cooperate? It's a good idea to paper pencil this stuff, truly. It's helpful to draw a little diagram. Yeah. How to create threads. So the best way to create a new thread is to follow these sort of, to mimic what was done in the demo code, right? So in order to create a thread, you'll create an object of type PT, the proto-thread control structure. You'll create the thread using this sort of syntax that we talked through a little bit. right? You'll call this macro PT thread, which takes as an argument the function which instantiates the thread and the argument to that function, which is always going to be a pointer to this object of type PT. You'll start it with a PT begin. You'll end it with a PT end. It'll have some setup stuff, maybe, that only runs once, and then an infinite loop that runs over and over again. When you create a new thread, the common mistake, the thing to remember is you are responsible for making that thread yield. So there's a condition in there by which the thread yields. In this example, there's a PT yield time for 1,000 milliseconds, which just yields for a second, runs, and then yields for another second. You might have a yield until some condition is met. But if you yield, then that thread consumes the CPU and no other thread runs. The interrupts will still interrupt it, right? So it can create some hard to track down bugs, depending how you have things set up, but no other thread will be allowed to run unless you have some yield condition. So you'll create the thread, and then down in main, you can pattern match here basically to see how to initialize your thread and then schedule it. Yeah. Yeah.
We need to make our own schedule, or does it come with?
You do not need to make your own scheduler. If you follow this, if you pattern match to how these threads in the demo code are being created and scheduled, you might create another thread called, say you wanted to create another thread called like my thread, right? You would, in this example, you would create a new control structure, maybe called PT underscore my thread. You would create a new thread here. Maybe you'd call it proto thread underscore my thread. Have it do whatever you wanted it to do. And then down in main, you would initialize it and add it to the scheduler. And then the round robin scheduler would just click through and ask and add it to the list of threads that it's asking whether or not it should run. Bruce, did you have a comment? Okay.
So is the proto thread, is it something that comes with the PIC, or is it an external library?
It is not PIC specific. So this proto, it all lives in the proto threads header here. And what you'll see is it is all C macros. Now Bruce has added a few things to the proto threads header file here to do things like yield for milliseconds, that kind of thing. In order to do that, there's a timer running. So in that sense, it knows it's running on a PIC32. But beyond that, this is all just C macros that don't know anything about the hardware that they're running on. So you could take a stripped down version of proto-thread, the default just downloadable version of proto-threads that doesn't have the Bruce editions that involve timers and such, and put that on an Arduino, and you could run proto-threads on an Arduino. Because it's just C macros, it doesn't know anything about the hardware. I've done that. It's kind of it's convenient. Yeah. Anything else? Okay. I was going to just talk about bird songs today, but we're out of time. Maybe I'll do that next time. It's nice, you know, I feel a certain obligation because these labs are cool. I like to explain why I think they're cool. And I didn't get to do that for lab 1 yet because there was so much stuff to cover at the beginning, but maybe next time. I'll take 10 or 15 minutes and we'll just talk about bird songs. Yeah.
Did that just mean what our class is?